Okay, so this is the pre-lab for proton NMR. Proton NMR works basically just like C13 NMR, which we did last week, except that you're looking at protons as the magnetically active nuclei, not C13s. And that's going to have some ramifications, right? So greater than 99% of all the hydrogen atoms in a molecule on Earth are protons, 1H. So it's a proton in the nucleus, 1 electron, or shared electrons. In C13, remember, the magnetically active nuclei is C13. That's only about 1% of the carbon you're going to find in molecules. And so that plays out into we get more information basically because we're looking at more protons. The sample's greater in proton NMR. And so an organic chemist, for a really simple molecule, especially if you have some idea of what the molecule might be, proton NMR can sometimes completely solve the equation. So as a routine, we're going to start doing lab work in a few weeks. When we're working in a research organic chemistry laboratory, routinely we take proton NMRs of everything. That's just sort of the first thing. And like I said, you know kind of what you're looking for, so that proton will tell you an awful lot. Okay, so let's get into it. There we go. So you saw this slide on the C13 pre-lab. Magnetically active nuclei aren't, they're just kind of randomly distributed. Earth has a magnetic field, but it's not strong enough to align the protons or the C13s the way we need them. So we have to expose the sample to a really strong magnetic field. We pump with radio waves. That's gonna excite all of the magnetically active nuclei, and then we'll listen for them to relax. And again, the information we get is the local magnetic or electronic environment of the proton or of the nucleus we're looking at. In this case, it's going to be protons. And like I said, you can kind of piece together everything about a molecule with enough NMR experiments. Okay, so again, we're kind of picturing the nuclei, the magnetically active nuclei, as these little, spherical magnets. They're kind of randomly distributed. We apply the magnetic field, and they all line up with that field. You can just think about this like these are like kayaks in a stream now, right? They're going to line up aim downstream. And then the excitement part is that the next available energy level, and I don't know if you've ever paddled a kayak in a river. The easiest way is to go downstream. The second easiest way is to actually go straight upstream, right? It's hard to cross because you got to kind of judge like where you're going. Why it's hard doesn't exactly hold, but it does hold that the lowest energy way for these magnetically active nuclei to behave in the magnetic field is to line up with the field. The next easiest way is for them to line up exactly against. And so when we pump the molecule, we line all the nuclei up, we pump the molecule with radio waves, the nuclei will go from aligned with to aligned against. And they can absorb only this amount of energy. Remember, that's how all of spectroscopy works. Molecules, atoms, can only absorb photons that match a physical transition in the molecule. And again, this energy gap depends on how strong the magnet is. Stronger magnetic field, bigger energy difference. Weaker magnetic field, less energy difference. But remember, for proton NMR, the point I want to make is this energy gap, which is the energy of the photon that's going to be absorbed, depends on the external magnetic field strength experienced by the nucleus. All right, that's going to be important here in a minute. So in proton NMR, unlike C13 NMR, we get a lot of information. So in C13, we got chemical shift. What type of electronic or magnetic environment is the nucleus in? Right, this is going to be our frequency. This is going to be the energy of the photon that gets absorbed. We got that in C13. And that's really all we got in C13. You could get some information about molecular symmetry. That works exactly the same way in proton NMR, right? If two protons are magnetically equivalent, they give one signal and one signal only. All right, but we get two other pieces of information in proton NMR, and both of these are mostly because the molecule's got tons of magnetically active protons, right? So almost all the hydrogen in a molecule is going to be proton, not deuterium. So we get what's called integration. And this comes just from the word integral, the calculus integral. It's not the political integration, it's the calculus integral. And boil it down, what this tells you is how many protons are causing that signal, right? So we integrate, we get a curve, right? So we get a signal, like let's say we get a signal like that. There's an area under there, which you can measure by integration. And the area of the peak is proportional to the number of protons making the signal. All right, so I think integration is probably the easiest one to pick up. I'll show you where you find that on the spectrum, but like if it says 2, well, it's all, in this class at the beginning, I'm just going to tell you how many protons are there. In real life, you would get like 0.78, and then there'd be another signal that might be, you know, 0.37, and that would tell you it's a 2-to-1 ratio. That, you know, the 0.78, there are 2 protons making that signal for every proton making the other one. That'll be clearer when we see a spectrum. All right, the toughest one, right, again, chemical shift is going to work like C13. You're just going to kind of have a table, and you'll slowly learn where in the spectrum certain types of protons show up. Integration is just how many signals, you know, how many protons are making that signal, right? If I've got a methyl group, it's going to end up integrating for 3. If I've got 2 CH2s that are identical, CH2, CH2, it's going to integrate for 4. If I've got a CH that's just by itself, no other CH like that in the molecule, and it'll integrate for 1. Splitting that I've got down here in blue, and hopefully the glare isn't too bad. On my phone, it looks fine. We'll see how it looks on YouTube. Splitting is the tougher one to get. All right, there's a rule I'm gonna show you that you can just like file away in your mind. Why splitting works the way it does is kind of important. And again, it comes down to all the protons in the or all the hydrogen atoms in the molecule are magnetically active. But splitting is what it's going to tell you is how many magnetically active nuclei, and in this case it's going to be other protons, are within 3 sigma bonds of the proton causing the resonance. All right, I'll spend a bit of time on that. So here is a proton NMR spectrum for the molecule shown up here. Am I on screen? I'm on screen. Okay, so again, chemical shift is going to work just like it did in C13 NMR, and I've kind of put down what you'll see here, right? So carboxylic acids, this is going to be stuff like that. So that's a carboxylic acid functional group. This OH, as you might get from the name of the functional group, is quite acidic. It hydrogen bonds really well. These are going to be broad signals, all right? More hydrogen bonding. I'll write it here. See if I can write it. And this is something to file away as well in your mind. Hydrogen bonded hydrogens in the IR and the proton NMR are going to give broad signals. And the reason for this is they're interacting with other molecules, so they're in a variety of different electronic environments, right? So, you know, if it's almost all the way over on the thing it's hydrogen bonded to, it'll have 1 energy. If it's really close to the atom you think it's bonded to, it'll have another energy, and everywhere in between, so the signal gets broad. So OHs, NHs, just like in the IR, tend to be broad. Then we get aldehydes. So this one right here is an aldehyde, CHO. And then you get protons on sp2 carbons, basically. And again, these are ballpark ranges. These are not like absolute, like it's at 5.2, so it can't be that. But protons bonded to to sp2 carbons will be sort of 6. I shouldn't even go down there. 6 to 8, really. 5. We'll call it 5. 5 to 8. Like I said, sort of in the middle, you're going to see protons bonded to sp2 carbons. Then you've got protons bonded to sp3 carbons. Bonded to an electronegative atom. Oxygen, nitrogen, chlorine. And then down here we've got protons bonded to sp3 carbons that are bonded to sp2 carbons. And then just, sp3 carbons bonded to sp3 carbons. So again, this is going to work, chemical shift is going to work basically just like it does in carbon NMR. All right, then you've got integration, and integration is just going to be a number at the bottom, and it's going to tell you how many protons are causing the signal. So this signal right here, 2 protons. That signal, 2 protons. 2, 2, 3, and 3. Okay, so I think that's fairly straightforward. Integration tells you how many protons are in there. Now we get to splitting. All right, splitting is going to tell you how many protons are within 3 sigma bonds of the first proton. Right? So the proton that causes this signal, how many protons are within 3 bonds of it? And the reason splitting works is, I think, really interesting. Right? So remember what we're doing in the NMR experiment. We're aligning all the nuclei with an external magnetic field. Then we're applying energy to flip that nucleus against the external field, and then we're listening for it to relax. So we're applying, this is a big horseshoe magnet, we're applying a magnetic field to this molecule. This is diethyl ether, right? So a 2-carbon group, CH2, CH3, that's an ethyl group. We've got 2 of these. This is CH2, CH3. So this is diethyl ether, flammable solvent that is it's an anesthetic, smells good. The CH2 here is magnetically equivalent to the CH2 here. The methyl at the end is equivalent there because you've got a line of symmetry here in the molecule. Okay, so the CH2 is different than the CH3, right? Those are not going to be magnetically equivalent. So we'll get a signal for the CH2, we'll get a signal for the CH3. If you think about integration, 2 and 3, the peak for the CH2 will be 2/3 that of the peak for the methyl group, all right? It'll be 2 and 3 or 4 and 6. If you think about chemical shift, these protons are on an sp3 carbon bonded to an electronegative atom. So they'll be down like 4-ish, 3 to 5. The methyl protons are on an sp3 carbon bonded to an sp3 carbon. They're going to be down like 1 to 2, somewhere like that. But what about the splitting? Well, remember, let's focus in on this signal, the signal caused by the CH2. It's going to experience this external magnetic field. But it turns out that each one of these protons is also a tiny little magnet, right? So depending on how these protons are affecting the external field, they're going to have some effect on these 2 protons, right? They could add to the external field, they could subtract from the external field. So the result is these 2 protons, if you look at the whole selection of molecules, remember, you don't have one molecule, you have like 10 to the 23rd molecules. If you look at all of them, some of them experience a field, that's all 3 of these are adding to it. Some experience a field that all 3 are opposing the external field, and some in between. I'll show that on the next slide. Right, so we start with a proton. So this is the proton we're interested in. We're interested in that signal. H is how we represent a magnetic field, so we're applying the external magnetic field. And so that proton would have a signal. Right now, the way it's pictured, it would just be a line. That proton would just give a line as a signal. But let's say it's got, didn't keep them in the same place. Let's say that this proton has one other proton within 3 sigma bonds, right? 1, 2, 3. Well, that other proton, so this little magnet here, could be opposed to the external magnetic field, or it could be aligned with the external magnetic field. We don't really know. And it could be both. And so we're going to get 2 different energies. So the observed magnetic field will be the sum of the external field plus the neighbor. All right? So in this case, we get 1 energy level. In this case, we get another energy level. So we'll get 2 lines, what we would call a doublet. So here's the rule. If you don't like all the physical description there, the simplest splitting, what we're going to hold with for unknown 1, is the total number of peaks in a grouping will be the near neighbors plus 1. So near neighbors are H within 3 sigma bonds. Right, so I said I've got that here. So here we've got one neighbor, so the number of peaks will be one neighbor plus 1, or a doublet. So we would actually see this as that, right? So this would be our spectrum. We'd see 2 lines for this proton. This would be the external field plus, where it's reinforced. This would be the external field where it's opposed. This winds up working out like Pascal's triangle. So if you look at these peaks, right? So if there are 0 neighbors, you get a line. You're always going to get one line for the proton. A magnetically active nucleus will show up in the NMR. If you have one neighbor, you get a 1-to-1 doublet, right? It's 50-50. Is that other proton aligned with or against the external field? 2 protons will give what we call a triplet. The most likely is one of those neighbors is aligned with and the other against, in which case you just get a line at the middle. But you can have them both aligned with, both aligned against, so a 1-2-1. Pascal's triangle, if you haven't seen this, basically you just add up, to get the next line, you add up the 2 above it. So 1, 1 adds to 2, 1 to 1, 1 to 1, 1 to 1, 1 plus 2 is 3, 2 plus 1 is 3, 1 to 1, so on. That's what the peak will look like. So here we have what's called a quartet. So the molecule here is CH2I. So again, we have a quartet for these 2, right, at 3. So the chemical shift is telling you that the protons are on a carbon bonded to an electronegative element, an iodine. And then these 2 have 3 near neighbors. Right, so these 2 protons have 1, 2, 3 protons within 3 sigma bonds. So 3 plus 1 equals a quartet. The methyl protons, these 3 here, have 2 neighbors. 2 plus 1 equals a triplet. Okay, so this is also called coupling. What's really happening is the magnetic field of these 3 protons is coupled to the magnetic field of these 2 protons. So if you have a CH2 quartet, you've got to have 3 protons somewhere coupled to them. And so the distance, and you don't really have to, if you're curious, the distance between the lines, that looks like an H, sorry, right? This distance there between those 2 lines is going to be the same here because they're coupled together. And so you can go in there and measure that, and it will turn out that you can figure out those are coupled. Here it's obvious, they're the only signals in the molecule. But if you have a big molecule, lots of different signals, you can measure this coupling and see that these 2 are connected. All right, so again, here's our proton NMR for this original molecule. This molecule fits this, so you've got chemical shift, integration, and peak splitting. You have to use all 3. All right, you can't just assume one of these is going to give you enough. If you just use chemical shift, you won't get there. If you just use peak splitting, you won't get there. If you just use integration, you won't get there. You have to use all of this data. In the next slideshow, I'll show you how to analyze spectra and assign peaks. So what I'd like you to do, if you want, before you watch the next video, is for every proton in this molecule, assign it to a peak. So remember, every proton has to show up in the proton NMR, and every peak has to have a corresponding proton. So if you just want to say, like, this one is that one, and this one is this one, that's what I'm looking for. I did them wrong there. All right, that's it.